In this module, we're talking about the Nernst equation. Well, we know that delta G is equal to delta G0 plus RT ln Q. We saw that back in the spontaneity topic. But we also have seen that delta G is equal to negative NFE. N is number of moles of electrons transferred, F is Faraday's constant, and E is the cell potential, which means that delta G0 equals negative NFE0. So if we just plug these guys in up here, we get this. All right, see that? And if we rearrange it a little bit by dividing both sides by negative NF, we get this. The E of the cell is equal to E0 of the cell minus RT over NF ln Q. Remember, Q is the reaction quotient. It's just like K, except not necessarily at equilibrium. So to get the Nernst equation, okay, we say, all right, we usually use log base 10 instead of natural log. So it ends up that to convert log base 10 of a number to natural log, you multiply by basically 2.303. So that's what this number here is. It just converts the log base 10 back to the natural log, or lets us write ln of Q as log base 10 of Q. Anyway, and if the temperature is at 298.15 Kelvin, that's Kelvin, then we can say that E equals E0 minus 0.05916 volts over N, and is the number of moles of electrons transferred, log base 10 of Q, where all I've done here is multiplied out the constants to 2.303 times R over F. That right there, well, these are both the Nernst equation. We use this a lot at 298 or Kelvin or 25 Celsius. So you should know, well, if you know this one, then you can always get this one. It's just more convenient to use this. But this is really the Nernst equation. This is what we're going to use. So memorize it. All right, so let's apply it. Let's look at this cell, this galvanic cell. At the anode, where oxidation is occurring, we have a platinum electrode. We use platinum, by the way, because it's inert. It won't oxidize or nothing will happen to the metal. It's just a carrier for the electrons. And what's happening is that in the anode half reaction, or the oxidation half reaction, iron 2 is being oxidized to iron 3. Now over here at the cathode, where reduction is happening, silver ion is being reduced to silver metal. And here we have the electrode made of silver, because it's just going to plate out right on there and make more silver. And there's our porous plug connecting the two. It ends up that the E0 for this cell is equal to 0.03 volts. If we look up the standard reduction potential for silver and that of iron 3 and then change its sign, we add them up, we get 0.03 volts. Now, applying the Nernst equation to this, okay, E equals E0 minus 0.05916, we're going to take this at 25 Celsius or 298 Kelvin. The number of moles of electrons transferred is just 1. 1. So that's N is 1 here. And now Q is going to be equal to the concentration of iron 3 over the concentration of iron 2 times the concentration of silver. So that's what Q looks like right here. Now, initially, the way we have this set up, we're under standard conditions, which means that everything's 1 molar. So if we plug 1 molar in for all these concentrations, we get log of 1. Well, log of 1 is 0. So this whole term becomes 0, and we have E is equal to E0. And so we have a positive, cell potential. The reactions, the electromotive force drives the reaction, and the reaction proceeds, and it proceeds towards equilibrium. So what's going to happen is, as this reaction happens, electrons go over here, we increase the concentration of iron 3, this guy gets bigger, we decrease the concentration of iron 2, this gets smaller, and because we're reducing silver here, we decrease the concentration of silver also, this gets smaller. Okay, and this whole quote Q here starts getting bigger. Next, the condition for equilibrium in terms of cell potentials is that E, not E0, but E0 is equal to 0. At that point, okay, so what's happening is this ratio here is increasing until it's equal to E0. So this is the equilibrium condition, and we know what E0 is 0.03 volts. So what we can do, right, is look, we can solve this equation for this ratio here. So all we do is we divide both sides, put 0.05916 volts. We get about 0.5. Log base 10 of this quantity is equal to that. Take raise 10 to both sides, we get that this ratio here, the concentration of iron 3 over the concentration of iron 2 times the concentration of silver, is equal to about 3.2 or so. What that means is, okay, that's at equilibrium. If we go back and look at the Nernst equation, so now we know that when this is equal to about 3.2 or so, E is equal to 0 and it's at equilibrium. If this number is bigger, if this ratio is bigger than about 3.2, then this whole thing, okay, being negative will be bigger than E0, and E will be negative, which means it's going to go back in the opposite direction until we get to equilibrium. If this is smaller than 3.2, then this number is smaller than E. We have a positive cell potential, and it's going to keep on going until it gets to equilibrium.